Thank you very much. I'm Jeff.
And I'm Greg.
Yep. And we're here to give a little talk and a retrospective on this work. So this work actually started out as an ICLR 2013 workshop paper with 4 of our co-authors working together. And in that work, we sort of explored a bunch of different sort of loss functions and techniques for optimizing word embedding representations. And really that was kind of the genesis of this work. And that work was cited by quite a few people. And one of the things that we discovered in that work was that the skipgram model, one of the few models that we evaluated in this workshop paper, really was showing better performance than some of the other ones that we worked on. So we decided to focus on that and really focus on the skipgram model and then some interesting sort of optimization techniques to improve the optimization of the word embeddings and added the ability to do phrase embeddings as well. And along the way, Ilya joined us as a co-author, which is great. And this paper has been cited by a number of people, as Sergey mentioned. One thing we've discovered, including source code and trained representations, really does boost your citation count. People have done this and used these downstream representations for all kinds of things, and we're very gratified to see that in the community. And we also want to highlight that 3 of our co-authors couldn't make it today. So Tomas, Ilya, and Kai couldn't be here, but on their behalf, we're delighted to be giving this talk. And with that, I'm going to turn it over to Greg, I think. Oh, no, we're older now. Sorry. Sadly, we've found more recent photos, and this is a test of time award, and yeah. time has passed.
Yes, I think we survived. We survived the test mostly. But so let's stand back and ask ourselves, what did we really learn from these papers? But before I get into that, I should probably stipulate that some of you out there rightfully say, well, we already believed these things before you published this work. And so for you, maybe this is really us reinforcing these points. Other of you might think that, well, the paper didn't really exactly prove this point, it just suggested it. So it foreshadowed it. We don't have any quarrel with whether it was reinforcing or shadowing or learning, and so we'll just put that aside for the remainder of the talk and talk about what we think are at least the themes that were in this work that resonate today. So the first point is that semi-supervised objectives have an incredibly powerful opportunity, and we think that they're going to be critical for natural language understanding going forward. We think that this paper shows that fast parallel and weakly supervised synchronization in computation really dominates over the sort of fruitless precision of tight synchronization. Focusing compute where it really helps and improves your learning of representations is what's most important. And tokenization can be used as a good trick to solve some nuanced problems. And then the last, and I think most important point, is that treating language as a sequence of dense vectors has proven to be really powerful, and honestly more powerful than I think we imagined when we started this work. So first on semi-supervised objectives. Why is this so important? Of course, almost all machine learning systems today go through some period of supervised learning. We're always going to use that, but there's too much to learn in the world to use supervised learning for everything. The promise of unsupervised learning, of course, is tantalizing, but has been difficult to implement in practice. And so semi-supervised learning, the ability to construct a supervised feeling data from a data set from an unlabeled corpus is really what we think works. So what's the basic program here? You begin with a large corpus of sequence data, say text, choose a random window within that corpus, and then algorithmically construct inputs and target outputs on the fly. And I want to underscore, I actually think doing it on the fly is part of what makes this method so powerful. And you have your choice about how you'll do it on the fly. You might be taking a word in the corpus and trying to predict its neighbors, which is the so-called skipgram model. You might be doing something like fill in the blank, or you might be trying to predict the end of the sequence, which is sort of the classic language modeling problem. All of these fit in this description, and if you repeat that a few billion times, it seems to work really well. But that's where we get into the hard part.
Yeah. So I think one of the things that we really explored in this work and sort of work we were doing concurrently with this is how effectively could we make sort of weekly synchronized asynchronous updates to a large model work. And Tomas, our first author, had been exploring these word embedding ideas on a single machine version that he implemented in C of both the skipgram and the continuous bag of words objective functions. And he actually did a fair amount of work to scale this up to be a very high performance implementation using all the cores on a single machine, so about 20 different cores at that time with almost no synchronization. So you just kind of blindly update the embedding that was sort of a large 2D array in memory. And then he was able to have about 20 cores on these multi-core machines simultaneously updating this shared representation and get, quite good embedding representations. Now, one of the things that we observed was every time we made the dimensionality of the word vectors larger, and every time we trained on more data, things got better, right? This is the lesson of a lot of the last 10 years of deep learning work is, scaling actually gives you much better results. Fortunately, a bunch of us were simultaneously working on a highly scalable system for distributed training of neural networks. So we decided to take the single machine implementation that Tomas had built for these word embedding questions and implement that in our distributed framework. And so the work we were doing kind of just a bit before this work was this large-scale distributed deep networks where we were exploring distributed training of large-scale models, mostly for vision and for speech. And really the motivation was how can we scale training on these systems to thousands of machines. We actually titled this Disbelief internally, so named because it was a distributed system, but also because a bunch of people were skeptical that it would work. And turns out it did work, which is nice. So the basic idea behind Disbelief is you have some set of parameters that are being represented on some set of machines, and then you have independent replicas of the model where you fetch the current state of the parameters, you do some computation on the model, and then you update the parameters by sending a gradient back to the parameter servers. And in large-scale setups, we were using tens to hundreds of machines to hold the distributed state of the parameters and hundreds to thousands of machines to hold the sort of independent workers of the model. And so that really meant you had 1,000 to 10,000 simultaneous threads kind of updating the model for the word embedding kind of work. And we were using 300 to 1,000 dimensional embeddings for a lot of things, 100K to million item vocabularies and even beyond for a lot of internal uses. It turns out you can make vocabularies out of lots of things, not just words, but particular videos that people have watched or all kinds of things and use kind of similar approaches than just language modeling. And now back to Craig.
And so this kind of provocative disrespect for locking and synchronization was the biggest single enabler of being able to do this work. But there were other things that we did that tried to focus compute to where it really actually made a difference in terms of model representation and quality. So for example, the meaning of tokens that is uncommon or that are uncommon is actually often more informative than common ones. And common ones are super easy to learn because you get a lot of chances at them. So we would probabilistically discard tokens related to their frequency, ignoring common tokens more often. And we applied that you could apply that both as inputs and in targets. Another thing that we did was we found that favoring objectives and models that were informative for the ultimate task, but were faster compute was better. And so in our paper, you can see we go through softmax and then an approximation to that through hierarchical softmax and then noise contrastive estimation, which is an even faster version. And then Ilya came up with negative sampling, which is an even faster version. We saw that quality went up every time that we were able to make it simpler and faster. We also found that you could use tools like tokenization to focus computation in the part that was interesting. One of the things that we used it for was to try to deal with phrase representation. So in English, compound concepts and nouns are often represented by multiple words. And so we just had a very simple heuristic that allowed us to build bigrams out of terms that were each individually not super frequent, but were co-occurring much more frequently together than you would expect. And many other authors have used tokenization schemes in these systems to great benefit, dealing with everything from contractions to declinations. And I just think it's important for us to not overlook that when we're processing text, we begin with tokenization. But then to the point of getting concepts to be n-dimensional vectors and how it is that this is so powerful. And I was actually trained as a neuroscientist, and so I saw this come up as ideas from a long time ago, from the 80s, about maybe concepts could be represented in a dense vector space, and that operators in that vector space, or geometric relationships in that vector space, actually meant something. But that was simply a conjecture. And then lo and behold, when we took these representations that we had learned in a semi-supervised fashion and investigated what was inside by, for example, flattening them into 2 dimensions using PCA, we found that there were syntactic relationships were represented geometrically, like these similar triangles representing the tenses of verbs, and that even arbitrary semantic relationships, like the relationship between countries and capitals or diseases and drugs, were also represented geometrically in this space as similar displacements. And that was really powerful. And then Tomas and Ilya were able to show that you could do these cute tricks, like solve analogies with simple vector arithmetic. By adding and subtracting vectors, you could see that sushi is to Japan as bratwurst is to Germany. Well, at least according to the language model. And in fact, you could even just do simple addition to imagine combining concepts and discovering what concept is nearby in this vector space. So for example, putting together Russian and river, you get tokens like Volga, river.
Okay, so summing it all up, what did we learn in these papers? Let's go back to the 5 points that Greg talked about in the beginning. So semi-supervised objectives applied to a large text corpora are, pretty important in natural language understanding. I would say definitely true today. Fast, parallel, weakly synchronized computation dominates in ML. Parallel, definitely. I would say larger scale specialized ML hardware has really enabled fully synchronized approaches to scale, even to the scale of models that we're training today. But I personally think that asynchronous approaches are going to make a comeback, because I think we're sort of close to where we're going to have to start reconsidering some of these asynchronous approaches to training very large models. Focus compute on the aspects of learning that need improvement. Yeah, simpler, more parallel methods win out over more complex, less parallelizable models, word-to-vec versus RNNs, transformers versus LSTMs. I think this is a good lesson as we're thinking about future improvements to these things. Tokenization can be used to solve seemingly nuanced problems. Yeah, more powerful models on top have actually pushed tokenization in the opposite direction of our phrase-based vocabulary, where we now have kind of subword sort of tokenization, and that actually has seemed to work pretty well for some of these models that have more complex attention mechanisms on top. And treating language as a sequence of dense vectors is more powerful than expected. Definitely true today. So we're really honored to receive this award. Thanks to the committee that selected the work. We're really honored. And thanks to our co-authors who couldn't be here today. And there's their pictures, Tomas, Ilya, and Kai. Thank you for this delightful work and co-authoring.
Were we still so young? Thanks,
yeah,
everybody.
We picked the younger ones.
All right, we have a few minutes for questions, so please submit your questions via Rocket Chat. You can also go up to the microphones. I'll take the questions from Rocket Chat first, and then I'll call on the folks at the microphones. We already have one question from our senior program chair. Do these analogies and vectors happen for more recent models? Do these analogies and vectors happen for more recent models?
Oh, so the question is, do analogies and vectors or arithmetic work on more recent, more elaborate models? And the answer is that it happens at specific levels of representation within what's being learned. But as we push tokenization down to smaller fragments of words, now you only have the original vector representations being for those fragments. But we think it still holds in a slightly higher level of abstraction within the network.
Jeff, you mentioned that you see a need for moving to asynchronous training approaches. Could you speak a little bit more concretely about that? What do you see as the biggest bottlenecks to, say, traditional 3D parallelism approaches or something of that sort?
Yeah, I mean, I think it's just a general sense that we're going to want kind of more lifelong and continual learning methods, and that those models might become kind of more modular, and that you're going to want to have asynchronous updates to different pieces of the model at kind of different timescales and different, not sort of try to orchestrate everything in a very large kind of modular model at a very confined, synchronous timescale. So it's really more that intuition, but I guess time will tell.
Yeah, so really sort of teasing apart the current paradigm where you do a big training run and then you're, sort of not learning anymore online, really, basically.
Yeah, I mean, I think it would be nice if we had continual learning systems that everyone was working to improve rather than these large artifacts we produce that are then used for downstream tasks.
Yeah. Thanks very much.
My question is to Mr. Dean. Compared to model sizes and compute power compared to the 10 years ago, now everything is on the insane level, right? So my question to you is, what would you label today as disbelief?
Well, I mean, I think in the current paradigm, we are using very large numbers of computers. I think the difference between today and then is the compute power per unit, per chip, or per machine, and then the connectivity between those machines is such that the synchronous methods actually work pretty well in, say, large TPU clusters or GPU clusters. I think part of the reason in Disbelief we had to use so many machines is the actual CPUs at that time were very slow relative to the amount of computation we wanted, and also the network links were quite slow. And so asynchronous methods really were a key thing that enabled us to make use of that hardware.
Thank you. For one of the main points, one of the main takeaways, you said that the difference between transformers and RNNs or LSTMs is kind of indicative of the fact that simpler models work better. And I'm wondering, I don't immediately see how those enforce that paradigm, because I find attention in transformers to be pretty complex and expensive.
I think you're right. It's not necessarily a simple method, but it is very amenable to parallelization, right? So I think you can actually take the attention mechanism and compute that in parallel for a very large number of tokens or a large number of representations. Whereas for recurrent models, that's more difficult because you have the sequential dependency on each step. And that really limits the amount of scaling you can do.
Okay, so it's more the parallel simplicity. Yeah, got it, thanks.
Thank you for inspiring work. So I was curious about these geometric relations in embedding space. And do you see any ways in which we can control, during training, we can control what kind of geometric relations we're going to end up with in embedding space?
Yeah, so we've done some work there, and I think it's actually an interesting area where you might want to have side constraints and additional objectives that you bring to bear. So, for example, we would also often do things like, okay, well, it's sometimes convenient for words to always have a unit norm, right, for other reasons, right? And you could do a constrained optimization in that way. I think one of the things that was striking to us was that when we first saw this property, we had done nothing in the space to induce it, right? But in more recent work, like for example in machine translation, when we were using encoder and decoder models, we were often trying to discover a vector representation for the entire sentence that could then be consumed by multiple decoders and still translated effectively. So I think often conceptually there's an opportunity to say a vector space is a human understandable space. You can analyze data in that space, and that's often one of the best windows into the mind of the machine. And how we do that at progressive levels of abstraction and transformer networks, I think is a great opportunity for new work.
Thank you.
Hi. You mentioned that one of the takeaways of the work was this stuff like hierarchical softmax and negative sampling and so on. But it seems to me that in modern models, we have started to limit our vocabulary more, so we can just do full softmax. Or do you still think that there's like this, there's a place for these sort of optimized softmaxes, or was that kind of a wrong turn?
So I think the point is that we realized that full softmax in this context bought us no quality, and that doing something that was simpler, less accurate, but either faster or more parallelizable, that was beneficial. So I think that's the lesson that's durable. And limiting vocabulary is one way to make the problem tractable. But I think in the fullness of time, we'll see that the value is to be flexible about what it is that, what are you learning? There's nothing magical here, in my view, about making the math perfect. It's about, is the system able to absorb knowledge from the data and use that to shape the representation?
Yeah, but I think your point about the vocabulary size shrinking makes the trade-off of doing the full softmax, much more tenable, especially on modern accelerators, which have, pretty capable matrix units.
Thank you.
Let's take one more question, and then we have to wrap up the session. So please go ahead.
Thank you for the talk. So to me, the idea behind word2vec is very similar to SimClear. But there is about 6 years between those two papers. Like, why you guys take so long?
So I mean, we were actually initially we were actually focused on aspects of work that were in the dense domain, right, where we were working with images and audio. And the move into text, of course, was very important. And literally the way that we started was by digging into literature like that. By, I asked one of the brothers, Bengio, what he would recommend, and said, you should look at the work of the other brother, Bengio. And that really is, it's important to say that these ideas, so many of these ideas, have been in the community for a long time. And I think that's part of the reason why a conference like NeurIPS is so important, because it's been running continuously throughout decades as these ideas have been evolving. And I think that there's always an opportunity to say, what idea from 6 or 8 or 10 years ago that showed promise then is going to shine today?
Maybe I would just add, the path in research is not always a straight line.
Thank you.
An excellent note on which to end this session.
Thanks.